Good morning, everyone. Welcome to another episode of XR Talk Show. Today is 2021, April 24th. And today we are going to do Lisp and Mathematica, Lisp and Wolfram Language. So this episode would be interest to those of you who are interested in programming language syntax design, or if you are a Lisp programmer, or if you are just interested in Wolfram language Mathematica, then you'll find this episode fun and informative. So good morning, Bart. Good morning, Jazzkey, and friends, Jason and Jason from France. Oh, hi, Jason Cutliff, and who introduced me to some technologies of microphone and audio. And good morning, this Russian guy. I don't know how to pronounce. Okay, so we are going to do 2021. Okay, we are going to start to code Lisp and Mathematica. I'm going to explain the isomorphism of Lisp syntax and Mathematica. Remember, let me tell you about a few episodes before. So if you look at my, just search for XR Talk Show and you'll arrive at my page. I did several episodes on Mathematica. Okay, actually, it's easier if we just go to YouTube, then XR Lee. Okay. I did a few episodes on Mathematica, and you would be interested to watch. Okay, where do I videos? Okay, let me show you. Okay, so starting with this one, XR Talk Show 2021, February 6th. Then since then, I did about 5 videos on Mathematica. So you may, if you are interested in Mathematica, start with that one. In fact, I have a kind of a YouTube playlist of my Mathematica videos. Okay, so anyway, let me begin. Okay, let's start to talk about this serious topic: Lisp versus Wolfram language versus Emacs org. So I'm going to show you the isomorphism between Lisp syntax and Mathematica syntax, and also the Lisp symbolic form and meta form. If you are a Lisp coder, you'll know what I'm talking about. And I'm going to explain the concepts of prefix, infix, postfix notations. And also, then I'm going to do some demo of typesetting in Mathematica. Then I'm going to show, eventually, I'm going to show how the similarity of you Emacs users, org-mod users, many similarities and functional equivalence, functional similarities about using Mathematica notebook, Wolfram language notebook, and org-mod. It can do, essentially, it's almost like org-mod. Everything org-mod can do, Mathematica can do, and much more actually. So let's begin. Okay, and lastly, let me show you. Let me tell you about this. Okay, so you go to XR. Yeah, let me get this out first. So you go to programming, you go to Wolfram language. So I have 2 videos there. You watch these 2. Then you go to download Wolfram language for free. If you are a programmer, if you just want to try it out, there are several ways, and actually they are officially free. Wolfram engine is free, Wolfram script is free. They are essentially the entire Wolfram language, so you can play and try it. You can also try it online. Okay, so copy that. Let's go back to Emacs and let's Wolfram language for free. Okay, let's start to do what we are going to do today. So first of all, so if you have seen Lisp, if you have not seen Lisp syntax, for example, this is Lisp syntax. This is my XR keys. You can see Lisp syntax is essentially lots of parentheses, almost purely nested parentheses. That is the Lisp syntax. Okay, and the Lisp syntax, essentially, you can generate the entire syntax. Let me just do the simple way. Okay, let me explain in the simple manner instead of being formal. Okay, so in essence, every Lisp syntax is this form. Okay, they are either an atom, f or 3, f or 2 or 3 or 3.5, or a string. Those are called atoms. So either they are atoms or they have the form a parenthesis, then a sequence of atoms, and it can be nested. So you can have that, or you can have that arbitrarily nested Lisp syntax. So this is, in Lisp languages, this is called symbolic expression. Okay, symbolic expression. So forget about the atoms. Basically, it just looks like that. And you can see here, check. Let me show you some. You see this. You see, it's full of nesting. Almost everything is nested brackets, parentheses, okay, round brackets, as the United Kingdom calls it. Okay, now that's Lisp syntax. Okay. Now let me tell you. So there's an isomorphism between Lisp syntax and Mathematica syntax. Okay. By the way, Lisp syntax, the use space to separate atoms. For example, okay. For example, you can have F34. There's a space in between. That means they are separate. So that's Lisp syntax. Now, what about Mathematica syntax? Let me type it. Okay. Wolfram Language syntax. Now, they are almost exactly the same. In fact, take any Lisp syntax, you can transform it in a systematic way to obtain the equivalent Mathematica syntax, Wolfram Language syntax. For example, so Mathematica syntax, let me show you. So it's gonna be like that. Let's simplify. Okay. Let's just say that. Okay. So how about this one? How do you do that in Mathematica? Simple, like that. You see, that versus that, that versus that. You see, in the Lisp syntax, you start with the parentheses, then you have several items inside. The first item is considered the function, and they are usually, okay, and that the first item is usually called the head of the expression. Head, like your head, head of the expression. So in this syntax, this thing is called the head of expression. As an actual example, if we go here, you see this expression. So you can see this, this real life Lisp code. This is the head of that expression. And similarly, in this expression, the narrator region is the head, and so on. Okay. So in Mathematica, okay. So anyway, let's go back to Mathematica. So that's the Lisp syntax, and this is the Mathematica syntax. So in Lisp, you start with a parenthesis, then you have a bunch of items, where the first one is the head of the expression. Now in Mathematica, it's similar, except you put the head in the beginning, then you put square brackets, then nest, all the same. So for example, okay, and also in Mathematica, you use comma to separate items. For example, let me write this. Okay, so F34 in Mathematica would be written like that, 3, 4. Okay. Now, but let me show you what were we talking about. What was I going to say? I forgot. So anyway, I hope you see the equivalence of, the kind of the isomorphism in mathematics. You kind of call that isomorphism, meaning that from one thing there's a map, one-to-one map that transform this one thing to the other thing and preserve their structure. So that applies to Lisp syntax and Mathematica syntax, meaning you can transform one to the other and preserve their structure exactly. All you have to do is move the head to the outside, then replace space by comma or comma by space, vice versa. So that is the okay. So that concludes the isomorphism thing about Lisp syntax and Mathematica. Now go back. Let's go back to my talk show page. Let's write it down. Okay. Let's write it down. Okay, show in browser. So we kind of explained the first part. Okay, so first explain the isomorphism of ideas, Lisp syntax, and Wolfram Language FullForm. Okay, so okay, that's one thing. Now I have an article, Concepts and Confusions of Prefix, Infix, Postfix, and Lisp Notations. Now you need to go to Concepts of Prefix, Infix, Postfix, Lisp. Okay, search for that. There, this article. Okay, Concepts and Confusions of Prefix, Infix, Postfix, and Lisp notations. Let me quickly go over these notations. So infix notation looks like that. This is your typical arithmetic, traditional normal math notation, 5 times 2 plus 3. Then you have postfix notation. This is actually a Polish postfix. So you say 5, 2, multiply. That means 5 times 2. Then you say 3, then you say plus. That means add whatever previous 2 items. That's a postfix notation. Then you have the prefix notation, which is kind of just the reverse of the postfix notation. So you say, so you kind of work from right to the left, 5, 2, and 5, then you multiply them, then you put 3, then you add 3 and whatever the sum of 5 and 2. That's a prefix notation. Then you have the Lisp notation. Now, that needs no explanation. We just did before. So then you have the typical functional notation in traditional mathematics. For example, sine, cosine, so you put f, then parentheses, then the arguments, okay? Then you have kind of so-called match fix notation. Now this is also very common. So you essentially you bracket everything together. Now you can see I have an example here, but most of you will probably familiar in any language, Perl, Python, Ruby, C, Golang, C++, C#, Java, they all have that. For example, array. 3, 4, 5. This is a typical array syntax in all these languages. Or you have a block of text, 3 plus 5. And semicolon and return. Let's say return. Okay, return. So this is these are called match fix notation. In a way, okay, there is actually no standard name for this kind of notation, but to be consistent with the infix, postfix, prefix kind of thing, we call them match fix. This is what Mathematica calls it. So when you have an array, example, array or list in most languages, okay, you have that, you just bracket them, and what does that bracket mean? That's kind of the operator, matched operator. So that means array. And for the code block or sometimes scope block, that similar match fix notation. Okay, let's copy that, let's cut that, and let's put that to here, so we have kind of a documentation of what we did today. There, match fix notation. Okay, so anyway, that's a digression, something about the syntax. But mostly I want to go back to explaining Lisp and Wolfram language, okay? So now we got comments, okay? If you have a question to me, put my name to it. Okay, so we have now explained the isomorphism between Lisp syntax and Mathematica syntax. Now, let me explain the full glory of Mathematica syntax, okay? This is when we are going to go to Mathematica. Let me demonstrate, okay? Let me show you. Okay, so 3 plus 5. Now, you see that 3 plus 5, 3 plus 2, right, equals to 5. Now, let's do 3 plus 1 equals to 4. You might be wondering, hey, Xia, you just said that Mathematica has, its syntax is fully bracketed, fully nested brackets. Then where do you get that 3 plus 1? What's going on? I mean, that should be invalid syntax, right? That's not Mathematica syntax. Well, let me explain. So, Mathematica syntax have these, it's purely nested brackets, just like Lisp, okay? However, it has a layer. It has a systematic layer, syntactical layer, that can transform any nested expression to kind of a more shorthand, or sometimes it's known as syntax sugar. But in Mathematica, it's very strict and systematic. Now, remember the word systematic. That means for any expression, let me explain. It's easier if I just start to show you, okay? So in Mathematica, how do you write 3 plus 2? You write it this way, okay? Plus 3, 2. Enter. You see, 7. Now, is that purely nested syntax? Yes, plus is the head of the expression, and 3 and 4 is the kind of an argument, and you have a comma that separates. So how do you do 3 times 2? Okay, times 3, 2, 2. Okay, enter. That's 6. Correct. How do you do so and similar for for divide and so on. Okay, so let's do a more complex example. So let's say 3 plus 2 3 plus 2 times 2. Okay, so 2 and 2 is 4. 4 times 3 is 4 3 12, 12, right? Oh, wait. Oh, plus, yeah. So 3 plus 2 times 2 is 7. Now, what is the, what is the Mathematica nested syntax for that? That is easy. Let me show you. Plus 3, actually, you can imagine what it is, right? Plus 3, then nested, okay? Then times 2 and 2, okay? Enter, 7. So let me make a point here. So you see these two kind of different syntax but equivalent. Now, let me emphasize this. They are syntactically equivalent 100%. In fact, whenever Mathematica, whenever you evaluate some expression, the first thing Mathematica, the kernel, the engine does is to transform all these infix or whatever shorthand syntax sugar to the full form. So you can see the full form here. So let me show you a bit different example. For example, list, okay? So let's say example list, okay? So how do you do list in Mathematica? This is a list, 3, 4, 5, or array, okay? In many languages, you call it array. In Mathematica, you call it list, okay? So let's say my list equals to 3, 4, 5, okay? Now you want to take the first element. What do? My list, okay? My list first element, the index starts at 1, okay? In mathematical languages, index start at 1, not 0. This includes Mathematica, MATLAB, Maple, Julia. Okay, basically any math-oriented language and APL. Okay, so how do you take the first element of a list? You do it this way. Okay, you see, my list bracket bracket 1, just like Python or Ruby, you know, similar to many others, except you use 2 square bracket. Now, so you might ask again, so wait a minute, this is not fully nested brackets. What's going on? This is, you know, this is also not, you know, they are syntax sugars. So let me show you the full form, okay? Let me do the same thing. So you set, okay, set x, okay, let's say, okay, my list, okay, my list, list. Then you say list 3, 4, 5. You see that? So this one is gonna be equivalent to that one. Okay, let's evaluate. Okay, let's not say 3, 4, 5. Let's say 3, 4. Let's say 9, 4, 5. Okay, evaluate. So that's a list. So this is the full form of that. Okay, so and let me continue. Let me show you this one. Okay, what's the full form of this? You know, take the first element of a list. Let me show you this way. Parts. Part. Okay, part. Then yeah, my list. Okay, my list. Then 1, the first element. You see. Here again, we have a fully nested syntax. Okay, let's evaluate it. 9, you see, because our first element is 9. So let me emphasize again. So in Mathematica, the Wolfram language syntax is a purely 100% fully nested brackets, isomorphic to Lisp. However, Mathematica has a systematic layer of shortcuts of sugar syntax. Okay, so instead of writing list like that every time, you can just use the, you know, curly brackets. Instead of when you want to set x equals to 3, instead of saying set brackets and x comma 3, you can just use the equal sign, you know, x equals to 3. So this feature is fantastic because this feature, this systematic syntax layer, allows you to have very convenient expressions. For example, if you are doing a lot math, you know, which is what Wolfram language is designed for. Let's say x third power plus y times x z squared. You know, let's say that expression. How do you do that in Lisp? Oh my God, that's gonna be, you know, if you're gonna write this in Lisp, it's gonna be a headache. For example, let me show you. So in Lisp, it's gonna be something like power x3, then okay, it's a pen. Okay, so let me show you how you might write that. Power plus, okay, actually we shouldn't do this in Mathematica because, you know, that's not Mathematica syntax. It's gonna show you lots of errors. So let's go do it in Lisp. Okay, so if you want to do this expression in Lisp, so common infix notation for polynomial, if you want to in Lisp form, would be, okay, so power x3 plus okay, so plus, then plus times, okay, no, it's gonna be painful and unreadable, times y, then okay, then power z2. So you see that versus that, you know, that. So you can see. So here is an important point, a side point. Okay, you can see here the importance of syntax in a programming language, because and that's a common complaint in Lisp languages. Over the past 40 years, many great Lisp pioneers have tried to introduce the Infix form, but it never became popular for one reason or another. But you can see why it is necessary, especially if you do a lot of math. You do want this kind of infix notation because this is just unreadable, especially when it gets complex. Okay, I'm going to talk about, especially when the expression gets complex. You know, you have the the formula for polynomial of second degree or series and sequence. You know, in this point it's unreadable. Okay, so now, so let's summarize. Mathematica notation has two layers. One is a purely nested form that's that's isomorphic to the Lisp syntax. Two, Mathematica has a layer that is a systematic short syntax system, which is 100% equivalent to the fully nested brackets. Okay, so let's cut that and put this into our explanation. Okay, showing browser. So we have explained several things about the Mathematica syntax. Now, okay, now here's something interesting in Mathematica. Now, if you are, good morning, Lucas. So I'm doing all right. Any comments, questions? Video check, audio check. So now back to Mathematica. So there is a way for you to get the notation. Okay, so all you have to do in Mathematica, you just type full form and any expression, and Mathematica will show what is the full form syntax. By the way, this purely nested thing, that syntax in Mathematica is called full form. Okay, so for example, let's say hold. Okay, 1 plus 2. So if you do that, it will tell you something like it will return something like that. But why do you put a hold there? Because if you don't put hold there, then 1 plus 2 will evaluate. It will become 3. So you just get 3. So, but if we do it this way, evaluate, you can see. Okay, let's not use hold. Let's say hold form. Okay, it's a bit. Yeah. Okay, let's use hold. So you can see Mathematica shows you this plus square bracket, and let me show you another one. Okay, let's say, for example, so I'm explaining the syntax of Mathematica. So for example, let's do a list 3, 4, 5. Okay, then Mathematica tells you that the full form is actually that. Okay, what about this one? This polynomial. Okay, we can do the same thing. Okay, so we paste the polynomial there. Paste, yeah. So evaluate, you can see the full form of that polynomial. Okay, polynomial of 3 variables. Okay, so that concludes our discussion about the isomorphism of Mathematica syntax and Lisp syntax and the layer, the full form of the Wolfram language, which Lisp do not have. Now, in 1960, when John McCarthy, who invented Lisp, he has the idea. Okay, he says that the Lisp syntax should be 2 parts. One is called symbolic expression, which is the nested brackets. Okay, let me write it out there. So Lisp syntax called, let's magnify a bit more, symbolic expression, aka SEXP. It's often known as sexp. Okay, that's a symbol that that's so this nested parenthesis is called symbolic expression. So when John McCarthy invented Lisp, he says that, okay, it should have the symbolic expression nested parentheses. He also says that it should have what's called a meta expression. Now, what is meta expression? It never developed, okay? It never got created because people got used to symbolic, the nested parentheses, and it just stopped there. So it's like indefinite delay. So it never happened, except many people tried to do it. But so in Mathematica, it happened there. Mathematica. So Lisp began in 1960. Mathematica began in 1986. So there's almost 30 years. So Stephen Wolfram, I guess I know he knows a lot Lisp. He borrowed the idea. He say, oh, that's a good idea. We need this meta expression. But in Mathematica, they don't call that. They just call it full form. Okay, so here's another interesting byway. Okay, segue. Why? So this is about the jargons. Jargons in computer science, the naming of things. So if you are a language creator, and there are many technical concepts, in programming language design, right? For example, lambda, currying, or arity of a function, and tail recursion, and lots of these jargons. So, but if you are designing a programming language, you have a choice, like which jargon among the jargons, which one should you choose? So here's one example where Stephen Wolfram made his decision, which is characteristics of his choices in Mathematica. Instead of calling it meta form or meta expression, he calls it full form. Why? Why does he make that decision? Of course, I don't know. I mean exactly what he thought, but I read enough of Wolfram's stuff. I can tell you why. Because usually the jargon, the choices of words or concept in Mathematica is chosen so that in the English language, the general English language, human language, it makes the most sense. Okay, so for example, compare meta expression versus full form. Which one is more intuitive? Like you don't, we are not asking for, specialized Lisp experts. I mean, just in general, in the English language, if you have this thing, you want most people to understand it. Which one is more intuitive? Full form versus meta expression. Okay, I would say full form. Yes, I would, yes. So this is just one example. Maybe this example is not the best example, but if you use Mathematica enough, you'll know. Actually, I'm trying to tell you something. So you get a sense of how things in Mathematica, Wolfram language is named. Usually they go for. Let me tell you another example that's more interesting. That's more illustrative. Okay. For example, in Lisp and in many languages, in Lisp, in Python, for example, and in Ruby, for example, you have the jargon lambda. Okay, lambda. What the fuck? What is lambda? What the fuck does that mean? Nobody knows, unless you are a programmer or computer scientist. In Mathematica, there's no such thing called lambda. Okay, you call it function. Okay. Let me show you an example. Okay, so let's do an actual example of Lisp coding. Okay, so let's start a Emac Lisp. Okay, so let's start a Emac Lisp. So I type lambda. Let's say I want to create a function that adds the two arguments. Okay, lambda yx, and here return will be. Okay, that's how I define lambda. Now you can evaluate this expression by, so you want to put two arguments to it. So let's see if I can. I'm not sure I can do it this way, but let's try. Okay, so lambda 2 and 3. Okay, So this, if we evaluate this thing, it should actually return 5 because it's adding 2 and 3. Okay, I'm not sure it will work in this. Yeah, it did. Okay, so actually let me show you the message buffer so you can see. Yeah, I don't know if you can see it. Okay, let's do it this way. Okay, so okay, so let's remove that. Let's prettify. Let's add a comment. This creates a function and apply it to 2 arguments, 2 and 3. Okay, it should return 5. Okay, that's what this is. Okay, now if we evaluate it, you'll see in this message buffer, you'll say 5. In fact, you see it here. Okay, so let's do it again. Evaluate, you see 5. So okay, so this is a Lisp. Okay, let's copy it, paste it here, prettify, show in browser, magnify, so we can we have our code there. Now let's show you the Mathematica equivalent to this lambda thing. Okay, now we are actually digressing because we are now talking about naming of functions and naming of things, naming of concepts, different philosophy, different predilection. Okay, so let me show you. So you want to create a function. So this is how you do it in Mathematica. Function, 2 variables, x, y. Okay, and what do you want to return? X plus y. Okay, that's one way to do it. And so, and you want this to be evaluated with 2 arguments, 2 and 3, right? So let's do it here. Remember, because remember the Mathematica form is like the function name, then bracket, which contains the argument. So the first part is a function now. So now you just say 2 and 3. Okay. Now evaluate it. 5. Okay, so that's how you do it in Mathematica. So what is the point here? Now my point is that you see the lambda jargon, Mathematica do not use it. You know, Stefan Wolfram Language. No, lambda. What the heck is that? That's not a good name. Okay, that's not a good name for the concept. It should just be called function. You know, so this is a good example that illustrates the choice of jargons, of concepts in programming languages. You know, depending on who you are Python. You know, Guido von Rossum created Python, or you know the Larry Wall who created Perl, or Gosling who created Java. You know, it's interesting naming of things. Okay. Okay, so that's about the naming of things. Let me write down this quickly so we have a record of what we've talked about. Okay. Okay, so naming of things. Side note, naming of things, naming of concepts and jargons. Okay. So this is interesting because you will see this is a common issue in computer language. I mean, in computer science and programming languages. You'll see this everywhere. Object, object, setter, getter. You have tons of those, or properties. Or for example, another popular, for example, array, list. That's 2 different names. Vector, array, list, vector, tuple. Depending on which language you are in, sometimes they mean the same thing, sometimes not really. Then you also have hash table, hash table, or dictionary, or map. In Python it's called dictionary, key value pairs, but sometimes they are called hash or hash table in Perl and Ruby, for example. In Java and JavaScript, it's called map, okay, key value pairs. So it's a naming of things, very interesting. Let me write down, okay. List, array, tuple, vector. Vector is a term Lisp uses, which is kind of equivalent to Python's tuple, which is kind of equivalent to C's array, okay, which is usually not the same as Lisp. The different languages, they have different meanings. Okay. For example, another example is hash table, dictionary, and map. Okay, so let's put that there. Okay, so shrink. Now we have our notes of what today's lecture notes. Okay, naming of things, that's a digression about, so let's go back to Mathematica. Now let me go back to, okay, so how long have I been talking? I actually have a lot more to cover. I've been talking for 40 minutes. Oh my God. Let me show you one more example of the syntax equivalent thing. Okay, for example, how do you write this? Actually, you should know. Okay, so let me write this by hand. Okay, in the full form. Okay, so let me just type it by hand. So let me do this quickly. Actually, we shouldn't waste time on this, but let me just. Okay, so. So you see, this part is exactly identical. It's syntactically equivalent, 100% to this part. Like I said before, whenever Mathematica start to evaluate the expression, the first thing, I believe so. I'm not exactly sure because I never worked with the internal, the implementation of Mathematica, but I'm pretty sure that's correct. Okay, so the first thing Mathematica will do a transformation of the syntax, transform everything into the full form like that. So these two are exactly identical. This is very different from the sugar syntax of many languages. In many other languages, Python or Scheme Lisp, sometimes you have two things. That's a sugar syntax for this, but their sugar syntax notion is kind of fuzzy, because they are not exactly the same. For example, let me show you an example. Let me show you an example, okay? The notion of sugar syntax. Notion of sugar syntax is not well defined. But for example, okay? I++ versus I equals to I plus 1. Okay? I forgot which one is before or which one is after. Plus I. Let's just say that. Okay? If I know you know what I mean. Okay? So don't nitpick. Okay? So in C and C++, the worst language of humanity, the worst screw up in programming industry, C and C++, the granddaddy of everything that is wrong in computing industry. They have this syntax, I++, In fact, that is why C is named C++ as a pun to this syntax. So what does I++ mean? It means add 1 to the variable I and return it. Okay, so it's kind of equivalent to this. Okay, I equals to I plus 1. So you say, normally, most people will say, that's a syntax sugar for this one, but not really, because these two forms, they actually compare to different things. Well, today the compiler becomes very smart. So today they may compare to the same thing if the context is right, but not always. That's a problem. You see, that's a problem. So anyway, my point is these two are not syntactically equivalent. The compiler doesn't. When the compiler sees this, it doesn't simply translate into that, then start to compile. It doesn't do that. These two actually will compile into different assembly code, depending on context. So that's so for the C and C++, smart smarties, they do obfuscated, C programming, they know the difference in detail intimately, and they are proud of it. Their code, their C code with very smart, impossible to understand, incomprehensible thing. Sometimes they'll use that because they know this is actually faster than the second one. So that's a problem. Anyway, my point is that syntax sugar is often not well defined, okay? But in the Mathematica situation, in the Mathematica language, they are syntactically equivalent, 100%. And the two layers, the full form versus the input form, they are 100% equivalent and systematic. Like there's no exceptions. There's no exceptions. By the way, Mathematica also have these, okay? I plus plus. Let me show you, okay? So let's say I equals to 1, okay? Enter, so I equals to 1. Let's say I equals to 1. Then let's say I plus plus, okay? Evaluate, okay, it returns 1, okay? Then let's type I again. It becomes 2. You see, Mathematica supports this syntax because it has shorthands to emulate so it becomes easier for you to learn in short, basically, because you came from C or you came from industry, you want to code Mathematica, so that makes it easy for you. So, but what is this form in Mathematica? Let me show you. Okay, so let's use the power of the full form. Then you have to say hold because you don't want to evaluate. Let's say okay, so let's say I plus plus. Okay, let's see what returns. Okay, it'll read. I don't remember exactly what set plus 1 or something. Okay, increment. That's a good name. Great name. So you see, this form I plus plus or X plus plus, is actually syntactically equivalent to this kind of function increment, then a variable name. Okay, so this is kind of in my view, this is a very beautiful part of Mathematica. Systematic and systematic, consistent. There's no exceptions. Systematic and 100% equivalent layers. And okay, so that's about that. Okay, so let me continue to the next thing I want to talk about. Actually, I spent a lot of time on this. I don't know if I'm too repetitive. Okay, let me get a drink and let's move on to the next topic, I think. By the way, why do I talk about this kind of full form thing, syntactic equivalence, for so long? Because in fact, this is one of the most important thing you need to understand about Wolfram language when you become advanced Wolfram language programmer. This becomes critical. You must understand almost by heart how almost every when you have, for example, after 1 year of experience programming Mathematica, you must become almost by heart, given any expression, you by heart know what is its full form. Why do you need to know that? So why? Because when you program Mathematica, you will be using symbolic pattern matching a lot. And when you do that, those pattern matching, they are not matching these sugar syntaxes. They are matching the full form. That is the full form that all your code using pattern matching is going to match with. Okay. There's a counterpart in Lisp. This is similar to Lisp's macro. Okay. So when you code Lisp, Lispers, they like macro, these macros. You need to understand, since Lisp doesn't have this infix notation, so you always see the full form. So my point is that when you program Lisp, you have the Lisp macro. Lisp macro, one of the important things for it to happen is that you need to have this fully nested regular syntax for it to work. Because once you have this, 3+2 syntax, your macro becomes very complex. So in the same way, when you become advanced Mathematica programmer, you do a lot pattern matching, symbolic pattern matching. You need to understand, be very familiar with how every expression is corresponds, is equivalent, what their full form looks like for example, like that one. Okay, that's why it's important. Okay, so now let's shrink. So let's let's write down. Okay, these are not syntactically equivalent, nor semantically equivalent. Okay, that's an important thing. I++ versus I equals to I plus 1, they are not syntactically equivalent. Of course they are not, but they are nor are they semantically equivalent. So when next time when you say, oh, that's just a sugar syntax of something, for example, that happens a lot in Scheme Lisp or in JavaScript, think again. Okay, what you mean exactly sugar syntax? Okay, like try to come up with a precise definition. And there, I mean, not just these examples, there are tons of other examples. Okay, but anyway, so let's go on. Okay, so let's go on with let's see where are we. I need to move on to next interesting topic. Full form, input form. Okay, analogous to Lisp symbolic expression and meta expression. Okay, start easy, explain this and that. Okay, show my articles. I've shown this. Okay, where is my article? I've shown these articles here. Concepts and confusions of prefix, infix, and postfix notations and Lisp notations. Okay, this article, there's quite a lot, so you might be interested to look into, because in this article I pretty much explained what I explained now. Actually, there's more. Okay, there's more here. Let's skip that. Okay, because I got other things I need to explain. I mean, there's a postfix notation and prefix notation in Mathematica too. Should I okay, so now remember, okay, so anyway, so I already explained these things, so let me move on to the next interesting thing. Actually, how long have I been talking today? 56 minutes. Okay, I think let that be that. So today this video is just about the syntax, okay? Because I was going to explain how Wolfram language does typesetting, okay? Then I was going to explain some analogous features of Mathematica notebook versus the org mod, Emacs org mod, where you can have outline, you can have headers, you can have outline, you can collapse them, you can expand them, you can export to HTML or LaTeX or any other things. You can export to lots of formats. In fact, that's exactly the same with Wolfram language notebook. Okay, so let's not do that today. So let this video today just be the syntax. Okay, I think that's it. Actually, pretty much any other thing. Exactly. So Jason, I believe Jason, you are also a Wolfram language coder, right? So yeah, the next thing I want to talk about the syntax is prefix postfix. Again, they are systematic. Okay, let me explain. Okay. So in Mathematica, so normally, right? So normally you write things like that, a function name, square bracket, arguments. But Mathematica has also a systematic way to write this expression without the square brackets. The fully nested notation is kind of nice because they show you the structure of the whole expression, similar to the Lisp's, nested parentheses. But however, as we explained, they are cumbersome. Sometimes they are just not good when you want, when you have a polynomial or lots of calculations. So besides sugar syntax for each, thank you, Farzin, for $5. And the question is, are you a citizen of Kyrgyzstan? Yes, I am. Yes. Next time I should, I think I've showed you my ID already. Okay, I'm a citizen of Kyrgyzstan. Okay, YouTube is going to ban me now. Okay, so Wolfram language has a systematic prefix notation. Okay, let me show you. Okay, so what's the example? Sine. Okay, let's say sine. Okay, now sine is a sine function. Sine pi equals to 0, right? Okay, let's do something fun. Plot. So we are doing some math. Plot sine x and x from let's say 0 to 9. Okay, and let's say 10. Show it. Fantastic. Now, so sine at 0 is 0, right? Everyone knows that. I mean, sine at pi is 0, okay? Sine at 0 is 0 as well. So this here is pi. Okay, let me show you something fancier, okay? So we want to do, I believe, ticks. Okay, 0 pi 0 pi, okay, 0 half pi. Actually, I should use a range. Okay, so let's do range. Range is like Python's range, okay? 0 to 3 pi, jump by pi over 2, increment by pi over 2, okay? Wrong. It should be axis labels. Okay, I hate this because I forgot the syntax, not ticks. I think it's ticks. Wait a minute. Wait, let me try this again, okay? There it is, okay? So you see, this is sine, so we change the axis, the label for the x-axis. Pi over 2, pi. Anyway. So that's a sine. So what's my point? My point is, let's go back to the sine pi, okay? Oh yeah, prefix notation. So sine pi, so I was saying sometimes the nested brackets, the fully nested brackets is kind of annoying, right? So one of the convenient way to avoid lots of nested parentheses is prefix notation. So you can say, instead of sine pi, you can say sine at pi. Okay, that is the prefix notation. Let's try another example. Sine at 1. Okay, let's see what's the value. Okay, so that's a symbolic result. Let's say sine at 1.0. Okay, so you got 0.84 something. So you can also write it as sine bracket 1.0. So you compare these two notations, sine at versus sine, bracket. So the at is a prefix notation, and this works for any function, not just sine. Okay, so in general, whenever you have x that can be written as x, f at x. Okay, so any function, any function that takes one argument, instead of saying, instead of using the square bracket, you can just write it, f at x. In the same way, you can have postfix notation. Okay, so so let me turn this into a cell format. I want to, what is it? Format style. Okay, old 8, old 7 text. Okay, so I forgot old 7 is not key. Yeah, okay, so and in the same way, so f at x, this is called prefix notation. And in the same way, there is postfix notation. Okay, f square x can be written as x / f. Okay, that's the post notation. By the way, this post notation is similar to Unix pipe. Okay, Unix pipe. In Unix is common. Something pipe something, that means return output and feed it to the next function's input and so on. So in Mathematica, you can think of it as a postfix notation, and in Mathematica the syntax is //. So again, this works for any function, not just any. So any function with one argument. So for example, sign. So for example, 1.0 / sign. Okay, enter equals to 0.84, just like before. So they and you can mix any of these notation, prefix, infix, or fully nested. You can mix them in any way. And so this is so again, let me emphasize, this is systematic. There is no exceptions. It's like the rules are very simple. You just like 1, 2, 3, 4, just for these 4 rules, and you can create the combinatorial variations of an expression is phenomenal. I mean, it's exponential. It's kind of so in the 1990s, the Perl people, the Perl programming language, they used to say there are more than one way to do it. They are so proud, of the Perl syntax, because it's like incomprehensible. There are 100 ways to write the same thing. But in Mathematica, they are systematic way, and there's actually more variations than Perl, than it is possible than Perl. Yet it's systematic and simple. So in fact, I have lots of articles on that. Let's forget about that. Okay, so let me show you. Yeah, okay. Let me show you some articles about this postfix notation and prefix notation, because they are very interesting. So you go to so first of all, you might want to read this article. Okay, concepts and confusions of prefix, infix, postfix, and Lisp notations. By the way, that title is a clickbait. This is written in 2006, before the word clickbait became popular. That's why they call me a troll. Okay, so anyway, but I also give you concrete, solid information about history of the history of notations, the naming of notations. Why what does it mean to be algebraic notations? I give you a clarity of understanding these kind of things. So this is one article. So that you go to my website, then you go to let's shrink, then you go to hacker code, then you go to syntax soup. Okay, here is a collection of articles all about syntax of programming languages, and there's a video I did before. Then there are, the point I want to talk about is I have 1, 2, 3, 4, 5, 6, 7 articles related to the pipe notation because there's so many things to dive into. For example, we talked about Unix pipe. Let me show you some example. You're familiar with Unix pipe, right? Yeah, I explained some of these things back in 2002. This is posted to the Mac mailing list. So anyway, let me show you. Yeah, here is the Unix, prototypical Unix pipe, in Bash, for example. PS, AUWWX, awk something, then sort, then xargs echo, that's typical. So pipe notation. So I mean, in Unix it's called pipe. So you can, from a notational point of view, this is called postfix notation. Why do I say notational point of view? Because they are different point of view. The pipe is actually, I mean, it's not just notation. It's also about how it does computation. So I mean, for example, in Bash, you don't usually consider these commands as functions because actually they have lots of side effects. But anyway, from a notational point of view, the Unix pipe is a postfix notation. Okay, so that's one article explaining that. Unix pipe as functional language. Okay, and by the way, that article has where are we? That article has the creator, the inventor of the awk language, Alfred Aho. He made some comments about what he think about pipe. So there's it's from an interview. Is there a connection? Someone asked him, is there a connection between the idea of composing programs together from a command line through pipes and the idea of writing little languages, each for a specific domain? So so he said, I think there's a connection. Certainly, in the early days of Unix, pipes facilitated functional composition on the command line. So you can see the idea of functional programming is there from the creator of the awk language. Okay, then he says you could take an input, perform some transformation on it, and then pipe the output into another program. Exactly. That is the paradigm of functional programming. Input, output, pipe, 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 pipe. The entire program is one giant pipe. That is actually in reality, in real world, that's kind of how functional programming works. As much as you can, it is. Okay, so anyway, that's about that article. Okay, so Unix pipe as functional language. Let me copy that and put it here so we have a record of what we talked about. So later on, you can see in my YouTube description. Okay, so I should stop soon. Okay, so let me return to the article. So I have like 6 articles about pipe, and let me mention this dot. Okay, dot notation. Okay, so this has to do, so first of all, let me tell you about method chaining, post operator, and object-oriented programming. Okay, so if you program in Ruby, or if you have programmed in JavaScript, you will be, or even if you have programmed in Java, you will be very familiar with this syntax, something dot something dot something. Okay, dot notation, sometimes known as method chaining. Okay, especially in JavaScript and Ruby. Okay, especially in JavaScript and Ruby, very popular. You see programmers talk about it all the time, but they don't know what they are talking about. Okay, so method chaining, again, from a notational point of view, that is postfix notation. Okay, postfix operator. In other words, the dot can be considered a postfix operator. Again, there's many details because for example, in JavaScript, when you say x.f.g, it's not actually not postfix notation. Actually, the x must return a object that must contain a method called f. Then you can x.f. Then if that returns an object, and if that object contains a method g, then you can .g. If it doesn't contain that, if it doesn't return an object and it doesn't contain the next whatever dot you cannot dot. It's gonna be an error. So it's not exactly a postfix notation. Okay, it's not. But from a notational point of view, you can see it is like a postfix notation. In fact, In fact, I have wrote a, let me show you, okay? I have wrote a JavaScript code that actually allows you to have postfix notation, postfix function composition, or like Unix pipe. So here's the JavaScript code. It's just 2 lines of code, okay? Actually, I'm proud of this code because I thought about this for a long time and come up with that. So anyway, let's go back. So I want to talk about this a lot to, just on this issue, there's a lot to talk about. So let me just grab the URL and post in my talk show so we have a record of it. Okay, so now you know about, let's close that. You know about, the method chaining, very popular in Ruby and JavaScript. And now as I explained, you see there's kind of a connection between the postfix operator and also a connection with OOP, because method chaining is not exactly a postfix operator, although syntactically it looks like it. It's similar, but it requires the OOP semantics. It requires they return an object and have the next method. Otherwise, it just doesn't work. Okay, so that's what this article is trying to explain. Okay. Then there are other issues. Okay, so there's a concept of namespace comes in. Okay, so namespace. For example, dot notation. So you have dot notation in JavaScript. But however, dot notation is not just, so on one hand, you can consider it as a postfix notation. But on the other hand, you can consider it as tied to namespace mechanism. So that's what this article kind of tries to explain, okay? So there are quite a few issues about this. So I have several articles on that. Then there's another question. So this question, dot before data or after data. So all these also have to do with OOP. They do not exist in functional programming. So for example, should you have object dot method name, or should you have? Sometimes it's different. Okay, I mean, for example, in Python you have string dot split. That splits the string. But in Python's regular expression, you have re.sub. Re is a regular expression object. So here, and in JavaScript, you have the same thing. So JavaScript, you have string.split or string.replace. You begin with a string, which is the thing you want to work on. Then you dot the method, what you want to do with it. But there's inconsistency. When you want to use regular expression, you have the regular expression first, then dot a method of regular expression, then you put a string. So there's actually two kind of inconsistent. So this is a design issue. This is a dilemma, kind of among two different design choices that's very common in object-oriented languages. So if you are a designer of a OOP language, what you gonna do? How do you avoid this inconsistency? In fact, it's a problem. There's no way to avoid it. It exists. This problem exists in Python, exists in JavaScript, exists in Java as well. The most typical example is number. Should you have a number dot plus, number dot times, number dot divide, like that? Or should you have a math class, math dot, then two numbers, math dot times two numbers, math dot divide two numbers? So it's very inconsistent, and this problem is very common in OOP. So this article, I'm trying to explain that aspect. So what's the so what's the whole thing? So the whole thing is about the dot notation, the pipe notation. There's many aspects of it. So okay, that's it for today, I think. So thank you, Fasin. And Danielle, people who can get over the syntax never actually get Lisp. That's incorrect, Danielle. I did like 2-3 videos, 1 hour each, explaining how incorrect is that statement. The statement is people who don't get over syntax never actually get Lisp. Okay, let me explain one thing as a retort to that statement. Okay, many Lisp phonetics, they will say, if you don't get over the syntax, you are not qualified to study Lisp. You don't get it because you think the parenthesis, nested parenthesis, is too much problem. But let me tell you, the nested parenthesis, actually, syntax is the most important thing, because without the nested parenthesis, the Lisp will not come up with the idea of Lisp macros. Okay, that's how syntax, how important syntax is. So, for example, if you don't have the syntax of APL, then it will be difficult to come up with the idea, the concept of array programming languages, which includes APL, Mathematica, Julia, MATLAB, okay, which is very convenient when you work on matrices or trees. Like almost, instead of working on one number at a time, almost all your, every time you call a function or operator, it's always on a bunch of numbers, matrices. That's called array programming languages, okay? But the first thing you need to have is kind of the syntactical, the syntax of APL. Once you have that, then that idea develops. And similarly, so what's a good point about the Lisp nested parenthesis syntax? The good point is that it shows a clarity between the structure and the semantics. Okay, the structure of the syntax, there's a kind of a correspondence of the structure of the syntax and the semantics. Okay, or sometimes they'll call, the nerds, okay, the C++, they'll say abstract syntax tree. Idiotic. Okay, so anyway, the Lisp, the good property about this Lisp syntax is that it gives you a clarity of from the structure of the syntax, you can see the semantics of the expression. Okay, so what's good about that? What's you gonna do with that? Well, then you started to develop, you start to think. This syntax give you, it suggests to you the notion of macros. Then you started to have the concept of macros, which all the Lispers love. A very great concept. Transformation of syntax, Lisp macros. That's what it does. Which Mathematica does far more. In a far more advanced ways, which then becomes symbolic pattern matching. Okay, if you expand the Lisp macro idea, what you get is symbolic pattern matching in Mathematica. Okay, but there are disadvantages. Okay, for example, if you want to do polynomials, like I explained earlier in the video, in Lisp it's a pain in the ass. It makes you, basically, your language is not suitable anymore. If you're gonna do polynomials all day and every day, your Lisp language is gonna be problematic. Unless then you have to create like a rendering system, like Maxima. Many computer algebra systems are written in Lisp. Anyway, I'm digressing too much. That's it for that. So Jason says the structure of Lisp is pure math. The syntax is optional. I don't agree. I disagree. Because anyway, so that's getting philosophical. Okay, that's it for today. If you guys like my stuff, donate, PayPal me, buy my stuff. Or buy my Emacs Lisp tutorial, or buy my JavaScript in depth. You know where to find it. It's everywhere on my website. You should see a Patreon link and my PayPal on my homepage. Okay, thank you guys. Bye. I'm gonna shut down in a minute, in half a minute. This is the opportunity for the last words. Did I miss anything I want to talk about? Syntax? Well, we covered enough. Yeah, so typesetting and orgmod features we're gonna talk about next time. Notebook and so-called reproducible research. Okay, we're gonna do that next time. And we have a lot to do, in my talk show. I think I'm gonna start to do regularly, like schedule almost every day, every other day or something, 3 times a week or 4 times a week. Yeah. So anyway, just watch for my YouTube channel. Right now, I haven't decided what to do, but anyway, I have, for example, topic notes. There's quite a lot of things I want to do about Emacs and Emacs Lisp, where, for example, I'm thinking about to create a XAR Emacs distro. So it's going to be like a competitor to Doom Emacs and Space Max. Okay, so you just download XAR Emacs and everything works out of the box. You have like my style of, maybe you'll like it, maybe not, but I think a lot of people want it. It's not difficult for me to create it. I can create it like almost the whole thing in 1 hour, in 1 hour or 2. Okay, but the problem is once I created it, put on GitHub, then the questions will start to come in. I become the tech support. Every day we'll say, oh, XAR Emacs doesn't work. How do you do this? How do you do that? Oh, yeah, tech support. And usually, from my past experience, I don't get money. Okay, maybe $10 a month, $50 a month. I cannot do that. I have to live. So anyway, I'm thinking of doing, XAR Emacs distro. Maybe, I don't know. I don't know about the money issue. That's an issue, right? So I don't know if I create that, it's gonna be tech support. I'm too old for that. Anyway, so bye guys. Yes, Jason. Jason asked the question. Let me answer that a little bit. Okay, so if you go to my programming blog, if you go to programming Lisp, there's a funny image. I did more than 2. I did several 1-hour videos on Lisp syntax. Okay, so there's a lot of detail, and I have like 50 or 100 articles about Lisp syntax. So one of them is what you just addressed or you claimed. For example, that's the infix notation, right? So you are saying many people has created infix notation, exactly, and I have a collection of them all. Let's see where. Okay, Lisp, what does symbolic language mean? Okay, Lisp macro change Lisp syntax. Lisp apostrophe quote came from MagLisp. That's a history of that apostrophe syntax. Mathematica versus Lisp syntax. XML versus Lisp syntax. There's lots of issues. Systematic syntax. Okay, there. Okay, so this article, Lisp Infix Syntax Survey. Here I collect from the beginning of Lisp 1958, all the pioneers of Lisp programmers who have created Infix syntax for Lisp. Okay, well, including Mathematica. Okay, So it's up to 2007, then Clojure, ArcLisp 2009. They have kind of variation. Then Racket Lisp, which also supports not just parentheses but also square brackets and braces. But although it's not Infix, but however there are several scheme packages that supports Infix syntax. Then up to 2015, the Clojure Infix, there's a project. Then quite a lot. So every 3-5 years, there are some Lisp programmers trying to do that. Then often they get ridiculed by Lispers. That's wrong. Okay, that's a code problem. So anyway, lots of articles, and in earlier, lots of examples. In fact, as I said, the very first Lisp created by John McCarthy, he wanted a infix notation called meta expression, which is the main topic we talked about today. Okay, that's it. Bye.